Okay, so today we are going to continue the chapter what we have started in the last class, and we have started to see some of the structure, crystal structure. Mainly in previous classes we have started to learn the molecular structure, uh, and also we have learned the molecular orbital theory, how the molecule can be. But now we are going to see how the crystal, that means if a molecule, not only one molecule, if many molecules come close together, in that case how it becomes a very large mm, bulk of the molecules. In that case how the molecules stay or how the molecules reside each other, close to each other, that has certain specific arrangement. So what is the specific arrangement that can be considered as the crystal structure? And in the last class I have mentioned about that around 90% of the molecules or compounds what we synthesize and what is found in nature, that is almost the 90% molecules are solid and they are crystal, and rest of them are uh, powder or something just like as ash or mess. So most of the time what the solid compound we synthesis or what we get from the nature, that are either, most of them are in crystal form. So we have learned several types of crystal structure as we have shown here. You can remember this one we have mentioned about. You can see the see my cursor mouse.
Yes. No. Yes.
You yes, I cannot hear you. You can see my mouse where I'm moving the mouse, otherwise it would be not so efficient teaching like this way. Anyone please respond that you can see my mouse or cursor, what are where.
Yes, Professor.
Oh, okay, thank you very much. Okay, in last class we have shown these types of structure, that where the parameters, that means what would be the size of the length or width or height of the crystal. Based on this parameter, value of the parameter, we have classified all the crystal structure into 7 different categories. So that is cubic crystal if all the parameters are equal. So I'm just going to give you little revision because that can be already you have mentioned, that is little bit difficult. However, just as we have mentioned, we can remember this by following some pattern. Here all the parameters are, that means a equal b equal c and alpha equal beta equal gamma equal 90 degree. So if you have any box, maybe I can show you something. You can see my video, if it is visible my video.
Yes, Professor.
Okay, then this is see the tissue box. If you can see the tissue box, then you can easily understand this is a hexagonal. That means we can consider, that means it has 6 different sides, 1 2 3 4 5 and 6. So if we consider all the sides are equal, that means this way and this way, if all the sides are equal, in that case we can consider exactly similar like this way. So if we have one atom here, another atom here, another atom here, another atom here, so we have another 4 atoms in the just 8 different corners, we have 8 different atoms. So if we have all the parameters are same, that means in that case a equal b equal c, then all the angles here also we have mentioned that all the angles, if we consider from this side, this is one side and this another side, so this angle is 90 degree. Another way, if we consider this side and this side, the angle is also 90 degree. Okay, so by this way we can see all the angles are of 90 degree, and all the sides are equal. So just now if we go from here to here, that means if A equal B, two sides are equal. That means this side and this side are equal. But if this side is not equal to the A and B, then we can see that we can consider that is tetragonal. Tetragonal, that means you are familiar with the tetrahedron. So in case of tetrahedron, you have length and breadth, or if you consider for like as a brick, that means we can have the brick, not exactly, because brick has also the length and width and height, they are different. So in that case maybe that is not the good way to represent. However, just if we consider that this side and this side are exactly equal, and if another side is little bit different, it can be either shorter or longer. So all other things are, all the angles are 90 degree. So in that case we can consider that is tetragonal. Now if all the parameters, that means A, B and C, are not equal to each other, in that case we are having, but all the angles are here same, alpha equal beta equal gamma equal 90, and here also same thing. Therefore we are having that all the, in this case this length and this length are not equal, or even not equal to this length, or even like this way, whatever we can say. So in that case we have found cubic, tetragonal, orthorhombic. Now if we go from here, either A, B, C are different, and also if one of the angle from here is not equal to 90 degree, in that case, or even if we have here alpha equal beta equal 90. So we have found here alpha equal beta equal 90, but now we would like to see that one of the angles from this, that means alpha equal beta equal gamma, one of the angles not equal to 90. In that case we can consider that is monoclinic. And hexagonal, if A equal B not equal to C, that means tetragonal and hexagonal. In that case what we will have, we have some similarity from this one to this one. A equal B not equal to C, and then alpha equal beta equal 90 degree, and one angle is 120 degree. We had one angle, all the angles are 90 degree, but here one angle is 120 degree. So that is as hexagonal. So 1, 2, 3, 4, 5, 6, you can see 6 points or 6 end in this side. Hexagon, all of you are familiar with these types of structure. And rhombohedral, already mentioned that if you push one side of the square, if you push just one side of the square, in that case you will have one angle which is less than 90 degree. So you can see this angle, if we consider this angle beta, so beta equal not equal to 90 degree it can be. So here we have shown another angle, we are showing here beta, but we are writing here gamma not equal to 90 degree. So that is not a big issue, just we are showing that one of the angles not equal to 90 degree. So here we can see that if we push all the angles, all the parameters, that means A, B and C, all the lengths A, B and C are equal, and then we are having alpha equal beta equal gamma equal not equal to 90 degree. And then here all the parameters including the angles are not equal. Therefore we have 7 different categories of crystal structure, and we need to remember this something for what are the patterns. If we have the cubic crystal structure, in that case we can have in last class we have calculated how many, what would be the size of the crystal structure or the length of the crystal structure, and also we have calculated the density of the crystal. So here we have what we have learned here in the case of simple cubic structure. In cubic structure we can have 3 different types of cubic structure. So what are they? Simple cubic and face centered cubic and body centered cubic. So what are they? We have mentioned that if the atoms are only at the end of my crystal, just if we consider here we have one face or one surface, we can put one atom here, another atom here, another here, another here. So one surface, and if we rotate another side, so we have another surface, 1 2 3 4. So that is the simplest structure, and already we have mentioned we can have only one atom. Can you remember what was the atom that we can have the simplest or simple structure, simple crystal structure, simple cubic structure? Anyone can remember? We have mentioned that one. In the universe, not too many atoms or molecules can have these types of structure. Only the polonium, you can remember, only the polonium molecule or polonium metal have these types of simple cubic lattice structure. Okay, then face centered. Face centered, we are having 8 different atoms at different corners. And then how many faces you have? Today I can show. Okay, yes, maybe I can use the marker to mark here. Just a second. This marker is always in my bag. Okay, we have, this is one phase. Okay, so if you have some molecule at the center of the phase, this is one phase. So previously we have mentioned we can have atom here, one atom here, another atom here, and this is another atom. So this is another atom. So if you have some center of the phase, this is one phase, so you can have at the phase centered. So if you have atom here, or even in this way, that can be, or even we can go for other way. So if you have any atom in this region, in that case that can be considered as face centered. And body centered, what would be? If we can put one atom just at the middle of this tissue box, that means at the center of the body. So this is our tissue box, and that is the cubic structure. So if you have any atom just at the center of this box, in that case we can consider body centered crystal. Tetragonal already we have mentioned. So we can have two different types of tetragonal. What? Simple, that means if all the corners contain only one atom, and then if we have one atom at the center, so we have here one atom at the center, that is body centered cubic, and this is body centered tetragonal. So we can have two different types, simple tetragonal and body centered tetragonal. So in this way we can have two different types of tetragonal shape. Orthorhombic we have mentioned, where A not equal to B not equal to C, but all the alpha, beta, gamma equal 90 degree. So in that case we can have four different types of orthorhombic structure. Orthorhombic, first simple, everywhere we have the simple. Simple, that means if you have a orthorhombic structure, that means all the atoms, that means all 8 corners of the cube, if all 8 corners of the cube are with only one atom, in that case we can consider that is orthorhombic, simple orthorhombic. Then if we go just only one atom extra inside the, or just at the center of the box or center of the crystal, in that case body centered. And then base centered. What is base centered? Base centered, now you have a, this can be considered as a base. So as I have shown, we can consider, so that can be one base, and we are not giving any other atom at this surface, or at the back side, or on the other side. So we are giving only two different atoms at the either this base or this base. So this atom just at the center of this base. Okay, so we can consider that is base centered, and this is as face centered. So face centered already we have mentioned here. So if we put several atoms at the one face, that means in the center of the face on of any face, in that case we can consider that the face centered orthorhombic. So just try to remember how many categories or how many types. I am not going to give you so many or I am not going to ask you the question how many or draw this structure, or what types of would be. Just try to remember what can be the types, how many types. And if you can understand while you are studying, that is fine for me, because we are not going to graduate in chemistry. So just you need to have the basic idea, and if you can understand, if you have these types of molecule anywhere, then just after observing this molecule you can remember, oh, that I had that orthorhombic structure. And if you have this idea that what type of orthorhombic, then that is very nice. So for the question, what I would say, just try to remember how many classes of orthorhombic clusters can be. There are four, is it? Simple, body centered, base centered, face centered. So if you can remember that phone name, that is for fine, that is for good for the question. And for everyone, try to remember the simple structure. This is one, this is one, this is one. So only these things you please try to remember, that would be fine for me. Any question? Something difficult, but I make it clear so that you don't need to memorize all the things. Okay, nobody is responding, that is not good. Okay, monoclinic we have already mentioned. In case of monoclinic, what would be the structure? This is our monoclinic. A not equal to B not equal to C, and alpha equal beta, alpha equal gamma equal 90, but not equal to beta. So if the beta is not 90 degree and alpha not, none of them, either length, width or height, none of them are equal. So in that case we can have simple. If we put 8 atoms, here one, here one, here one, here one, all of them, 8 corner will have 8 atoms, and just that would be simple. And we can have another type, base centered. So we have 8 atoms, that is monoclinic, and we have another few atoms at the base, either in this base or in this base. So base centered. Triclinic, it has nothing else except the simple, either even for the hexagonal and rhombohedral, all of them have only one pattern, so there is no other options. So please try to remember, we have three different classification for the cubic: simple, face centered, body centered; and tetragonal, we have simple and body centered; and orthorhombic, simple, body centered, base centered, face centered. This is four different categories. For monoclinic we have only two, and triclinic, hexagonal, rhombohedral, we have only one category. So crystal structure of graphite and diamond, all of you are very familiar with these types of structure, and you are familiar that the melting point or the boiling point of diamond is very high, and it can be used to cut glasses. All of you are familiar with this? If anyone here, can you hear me?
Yes, Professor.
But
Yes,
nobody is responding. Okay, so that is the disadvantages that if you are online, then I cannot get response from you, so I do not like to have the classes online. However, just maybe for today, or in case of some emergency, we may have some online classes, but I I think it is better to have the class in the physically. Anyway, so you are familiar with that the term that the graphite is very soft. And what is graphite? You have example in your hand. Anyone know about the graphite? What is the best example for graphite? This is in my hand. Can you see?
Pencil.
Yes. So how the pencil works? Anyone have the idea how the pencil works? How the pencil works and how graphite is used to cut the glass. Glass is very hard, so and also very brittle. So, but you can use graphite to cut the glass, and you cannot use graphite to cut the glass. However, what are the components for graphite and diamond?
Carbon.
Both of them are carbon. Just they are different in structure. And this graphite is very soft. Soft means that the melting point and boiling point of the graphite is very low, while the melting point and boiling point of this diamond is very high. So why it can be, or why it has so different characteristics?
Professor, diamond has like a sparkle, like it radiates light or something like that. But where
Yes.
graphite is not like that. Like it's not bright.
Okay, yeah,
Bound.
that is the why it is so costly. Why we can consider the diamond is so costly. So my question was not that way. So you have mentioned something that is difference, but I want to know why we can use diamond to cut the glass, and why we cannot use the graphite to cut the glass, or even how the pencil works. So if you don't know, that's fine, no problem. I will tell you. Let's see. While we are writing using the pencil, how it works. First, let us see. While we are writing using the pencil, just when I slide down, when I slide down the pencil over on a paper, what happens? Some of the layer, some of the layer of the pencil, that means some of the layer of graphite, is contacting or attaching with the paper, so that it makes some line, or it can be used to write down. That can be possible only as the structure of graphite is like this way, that is hexagonal, and it is kind of layer. Here you can see this is one layer, this is another layer, this is another layer. So when we slide down the pencil over a paper or anywhere, if you slide down the pencil, then few layers, this is one layer, this is another layer, this is another layer. This way we have millions layer of graphite in this pencil. So when we are sliding this pencil over the paper or anywhere, in that case some of the layer of graphite is attracting the paper, or it is mm, staying on the paper, because it has some attraction force with the graphite and the paper. However, if we consider the structure for diamond, that is hexagonal and layered. Hexagonal, why you have considered? This is like as benzene. You can see this is one carbon, this is another carbon, this is another carbon, this is one. Sorry. So we have 6 carbon atoms, and we have uh, all the system. This looks like as benzene, but not exactly like as benzene. Something similar, but the attraction force between this layer to this layer, that is very low or very less. That means the attraction force, if the attraction force between these two different layers was very high, in that case it was not possible, or it would not be possible to write on the paper. So as the attraction force between this layer and this layer, here you can see these dotted lines, you can easily understand these dotted lines are represented the very weak attraction force. Therefore when we slide the pencil over a paper, then few layers, either this layer, one layer or two layer or few layers, when you press hardly, then you can have many more layers. When you press lightly, then you can have either one or two layers, or maybe little bit more layers. Anyway, so when you slide the pencil over the paper, in that case some of the layers, let us consider that is the upper part of the pencil and this is the lower part of the pencil. So when you slide the pencil, then this layer will come in contact with the paper, and this bonding, this low attraction force bonding, that will be removed, and that will go, or that will come into contact with the paper. So we will have this carbon, black carbon on the paper, so we can see something has been written. But in case of diamond, the structure is face centered, cubic face centered. This is hexagonal and this is cubic face centered, what is very rigid. And the structure, as these types of structure is very attraction force, you can consider here the attraction to this carbon, how many carbons are attached to this one, this carbon is attached to this carbon is attached to this. So we have only two carbon attaching clearly, and maybe we can have three. This carbon, if we consider this carbon, it is attacking to this one and this one to this and this to this. So we have three carbon atoms making, or one carbon making the very strong force with the adjacent three carbons. But here we have very less attraction force. That means within this layer they have very high attraction force, while within this layer to this layer the attraction force is very low. Therefore it is very easy to slide one surface or one layer by layer. But here each carbon is attached with four different carbons with very strong force of attraction. Let us see. If we consider this carbon atom, this carbon is attached to this carbon, this one is attached to this carbon, this one is attached to this carbon, and then this one is attached to this carbon, and that structure is very fixed. Here you can see for this carbon we have here this is attached to this on this, and this one with this. So that type of structure is very rigid, and it is very hard to break these types of bond. The attraction force between these carbons is very high. Therefore if we want to break this bond, that tetrahedral bond, so these types of bond breaking you need lot of energy. But here you don't need huge energy, just if you push by your hand or with something else, just that is enough to break these types of layers. That means you can break this bond only, not the inside this bond, you cannot break this bond. So when you are breaking this bond, then one layer or two layer can be separated, so that the graphite easily we can write down on a paper, but using graphite, so the structure for this one is, or diamond is very hard or rigid, so that the attraction force is very high. Now how we can use diamond to cut the glass? That is because to cut something, if you want to cut any vegetable, you need some knife, is it? Why? Why we can use knife to cut the vegetables? Because knife is very harder compared to vegetables, and it has some sharper edge. So if you want to cut the vegetable, you can use the knife that is made of steel, and that the melting point or boiling point of that knife is quite high or quite higher compared to the melting and boiling point of vegetables. Therefore we can use these types of knives or whatever to cut the vegetable. Similarly, as this compound or this diamond has very high melting point and boiling point, and the structure is very rigid, therefore we can use this diamond to cut the glass. Just if you put one mark on the glass and then just bend it, you will see automatically it can break down or it can cut. Therefore, so now you are clear why we can use pencil to write down. Anyone have any question? Nobody? I want to ask.
No question, Professor.
No question. No question. That's good. But if you really understood, did you?
Yes, Professor.
Okay. So that's fine. So we can see that the crystal structure for graphite and diamond are quite different, and that the structure for graphite is hexagonal and it is stays in the layer. Therefore the attraction force between these two layers is very less. Therefore we can use the pencil to write down, and this can be used to cut the diamond glass or very hard things also. So we have calcium crystallizes in a face-centered cubic structure. The edge length of its unit cell is 558.8 picometer. What is the atomic radius of the calcium in this structure? Calculate the density of calcium. In last class we have calculated something similar like this, isn't it? We have one example here, this one, is it? The edge length of unit cell, simple cube we have mentioned what is the length can be. So simple cube we have found that this is one atom, center of the one atom, this is another atom. So these two atoms are touching adjacently, so just touching each other. So there is no visual space between these two atoms. So this is the, if we consider, this is the length of the crystal, or that can be considered also the length of the crystal. So what would be the size of the atom or radius of the atom? Here we have two atoms, that is simple cube structure. But if we have something different structure, that means if we have any face centered or body centered or something else, in that case we need to think how many atoms can be. Just if we consider this is the length or this is the length, then how many atoms can be placed in between the edge or the length these are. If we consider that is the length of the cube or crystal, in that case we need to think or we need to see how many atoms can be kept just through one length. So here we can have only two atoms, therefore one, this is up to this, another this atom. Therefore the radius of this atom, so radius of this atom is just half of the length of the crystal. So here we can have the radius of the polonium is R equal L by 2, not 1 by 2. We can write down L by 2. We can, this is the L and 2, so divided by 2, because we have two radiuses, two atomic radius. From here to here one atomic radius, and then from top to this middle this is another atomic radius. Therefore we can consider that the radius of one atom would be half of the total length. Okay, that means 1 by 2 or L by 2, you can consider anything. This is, we have mentioned L equal to R. Similarly, we have calculated the density. So how we can calculate the density? As already I have mentioned, that means you are familiar with the word, or sorry, the term, the Avogadro's number, or 1 mole. 1 mole. So for any substance, if you can calculate the mass of one atom, then you can easily calculate the density of that atom in crystal. Okay, so we have calculated the density. We are familiar with the term density equal mass by volume. So you need to find out the mass of one atom, and you need to find out the mass, volume of the crystal. So volume of the crystal and mass of the atom, how many atoms that you have. So we will have the mass of atoms, and then we will calculate the volume of the crystal, therefore we will find out the density. Just okay, so in that case we have one question. Calcium crystallizes in a face-centered cubic structure. So the edge length of its unit cell is 558.8 picometer. So we have mentioned that face-centered cubic structure. That means face-centered cubic structure, what can be? This is our face-centered cubic structure. Is it? So if this is the face center, that means length equal, all the lengths are A equal B equal C. So this length or this length or even this length, that are same. So we can have, as already we have mentioned for the previous one, simple cubic. In that case we had the length of the atom as length of the crystal just 2 atomic radius. Exactly similar thing we will have here. So the edge length of the crystal is L, which is equal to the 2R. That means atomic radius of 2 calcium atoms. Therefore we can easily find out what is the then radius. Radius equal 558.8 divided by 2 picometer. So we are getting, just if you divide by this, I have the calculator, if you have, you can calculate 558.8 divided by 2, so 279.4 picometer. That is the length of radius of the calcium atom. Now you can calculate the volume of the calcium atom, because you are familiar with the formula of a sphere. You are familiar with the formula, I have mentioned 4 by 3 pi r cube. That is the formula of volume of the atom. So 4 by 3 pi r cube. R is the 279.4 picometer. You can convert into meter. Then you can multiply with the 4 by 3 multiplied by pi, and then you need to cubic for the r radius. So we can calculate the radius, volume, and then we can calculate the mass of one calcium atom. How we can calculate the mass? Just we will have what is the molecular weight of calcium? Molecular weight of calcium, anyone can remember? Nobody?
40.
40. So just you can answer spontaneously. I have asked the very simple question. So we can calculate the mass of one calcium atom. That means how many? 6.023 into 10 to the power 23 calcium atom have the mass 40 gram. So for one atom, how much? Just that is the mass of the calcium. So by this way we can divide the mass with the volume what we have calculated previously, and then we can get the density. That would be, now which structure will be closely packed? We have different types of structures, but which one would be the mostly closely packed? either the hexagonal, cubic or tetragonal, whatever. So how you can consider, I have another, this is box maybe. So if I try to put some bigger balls, what the balls you have in the display, if we have some balls, then if we have bigger balls, in that case we cannot keep too many balls inside this box. Okay, so in that case what will happen, there will be lot of spaces in between two different balls. So we can have some spaces when we put one layer. Maybe this is one layer, this is another layer, this is another layer. So if we have a larger space in between two separate layers, then that the open space where there is no atom, that can be considered as void or open space. So I have used one term, void. So that is the open space where even you can consider this is one surface. This what is the color for this one? This is gray or light yellow? What one? I'm little bit color blind. That means not color blind. I cannot rename, or I cannot name. What is this? This one color? Pink. Is it?
Violet.
Violet. Yeah, that's good. Violet. So, and this one?
Cream color maybe.
Yeah, that can be. Normally, I have one very interesting picture, that normally the boys see just the broad range of the color, either red or black or something like this. So, but the girls can see huge difference between the color. So, even
Yeah, women can do very much classification
yes.
of colors.
Yeah. So here we have this, if we consider this cream color or just light yellow, this one. So you can see some of the space here. Just if I consider, you can see the green balls through the cream colors, cream balls. Through the cream balls, you can see the green balls behind. Therefore, what does it mean? We have some open space in between these surfaces. We have kept the balls as closely as possible. That means this ball is touching this ball, and this one touching this ball, even this one touching this ball. So we have no more spaces that we can put another ball. However, we have some open spaces in between these three balls. We can have one space here, we can have here another space. So if the space, how much space is empty, that can be, if you have the very large open space, then that is not closely packed. That means if you have more atoms and very less amount of open space, in that case that is not closely packed. And if you have more open space, then sorry, if you have very less open space, then we will consider that is close packed. So compared to this one, if we consider, so this one can be even more closely packed. So we cannot have too much space in between this layer and this layer or this layer. So for here we have very large space. Here we can see within these two layers we have very large space. Here we have, we can put these two, between these two layers. Now the space has been even reduced. Now if we put these cream balls over the green balls, just if you put one above another, other way, if you rotate little bit, because maybe we can consider we have one hole or one lower portion. So if we rotate the ball, you can remember where we can put the eggs in the refrigerator. We have one up and down. That means you can where in the market how the eggs are sold, or you can see 30 eggs are put in one case. So if you want to put egg in that case, you cannot put the cases very close, but while there is no egg, you can keep all the cases very close. That is okay. So now if you have some eggs in between, this is one case, this is another case. So if you have some egg, then this case or these eggs, sorry, this case or this case cannot come close together because we have another uh, eggs in between. Therefore, while we do not have eggs, in that case we can keep the cases so close that can reduce the size, or the total size of the box is very thin. So that is very close. But while we have something in between, in that case the case becomes very large. Therefore here now the space has been booked, or space have been reduced by the other molecules or other atoms. Therefore it has kept, or it has occupied all the spaces available, or most of the spaces available. That means in this case we have a lot of open space. Now for here we have very less open space. Therefore this is more closely packed compared to this one. Voids and holes, what I have mentioned, that voids or holes, that means if, as already I have mentioned, we can see the green balls through the cream balls, therefore that the place where there is no atom or nothing is there, that can be considered as void or holes. So tetragonal hole, how we can have the tetragonal hole or tetrahedron hole, that little bit matter of thinking. If you have, that can be little bit difficult to show up. So here actually we have 4 different balls, but we can have the hole. If I could really show you the structure making different balls, making of many balls, in that case you could realize that what is the shape of this hole. Actually this is not like as a hollow. If we consider, if we want to put these types of rod or something, or one pen, that cannot be, because that is not homogeneous. Somewhere the space is very large, somewhere the space is very small. Therefore we can have the hole in different shape. So based on the structure of the crystal, we will have different types of shape of the void or holes also. So even you can see some of the holes, you can see the background through the, from here if you consider just this way, this where is my pointer, you can easily find out. We can see some hole, that means you can see the background. That means none of the balls are at this point. That means this hole is very hollow. Now if you have another layer, in that case we may have closed the hole. Otherwise if we have 2 layers we can have some open space. But if you have many more layers, in that case the layer by layer, the hole and the hole or void can be in different shape. Therefore we can consider the voids or holes can be tetrahedral or tetragonal, tetrahedral, so octahedral also, different types. If you have so many, that means we have how many atoms here, 1 2 3 4 5 6. So if you have 6 atoms are coming together, so in that case all of them are just touching each other. In that case we can have very small hole that will be in shape of octahedron. So we will have the octahedral hole. Now, if we want to know what would be the structure for ionic crystal, till now we have learned about the structure of metals. Now, if we want to see the crystal structure of different molecules, that means we have several ionic molecules like as sodium chloride, potassium chloride, and many others. And most of the ionic compounds are solid or crystal. So we can have also the structure or fixed structure for the ionic crystal or ionic compounds. So ionic crystal consists of two or more different types of ions. Definitely we will have at least two. Sodium chloride, we have sodium of one size and shape and with different one electropositivity sorry. And in case of chloride, we have another atom with different shape. So ionic crystal consists of two or more different types of ions. Previously we have shown all the atoms are of same size, same shape, as already we have shown this type. All the carbons, these carbons all are same. This carbon everywhere all the same. So we have considered that the crystal structure of some metal or some element. But if we want to see the crystal structure for any ionic compound or any ionic crystal, so we are familiar with the term the ionic crystal or ionic compound that is made of two or more different types of ions. That can be packing of such ions is complex compared to the metal structure. That is even little bit harder compared to the normal what we have seen for the metal structure, because in case of metal structure all the atoms are of same shape and same size. Therefore easily we can understand or we can calculate what is the radius and what is the density, because if we know the type of the crystal then we can easily calculate the density or the radius of the or length of the crystal. But now in case of ionic crystal we will have different types of atoms. Sodium chloride will have sodium atom and chlorine atom. Potassium chloride will have potassium and chlorine. So we will have different types of ions having size different. So packing of such ions is complex compared to the metal structure. Monoatomic ions behave as charged sphere with same attraction for the opposite ions in every direction. Monoatomic ions, what we have mentioned, that means the metallic structure. Monoatomic ions behaves as charged sphere with the same attraction for opposite ions in every direction. So if you have any atoms of same size and same shape with same electronegativity or electropositivity, in that case it will behave like everywhere all the atoms are on same shape and same size, so they will feel similar attraction everywhere. So now structures stabilized by maximizing coordination number and contact between oppositely charged ionic spheres. So if we consider for ionic crystals, how the crystal become stabilized, that is possible only when the crystal structure has the maximum coordination number. In last class I have mentioned about the coordination number. Anyone can remember coordination number? Please, coordination number, what is?
Coordination number half into sorry bonding. Is it bond order,
No,
Professor?
I'm asking for coordination number, not the bond order. Okay, if I go back to the structure, then you can easily find out where I have mentioned the coordination number. Here, this one atom is bonded to
Yes.
six different atoms. Therefore, the coordination number for this atom is 6. That means now you can tell the definition. I have changed that slide. I have mentioned that the one atom can have bond with 6 different atoms. Therefore, the coordination number for that atom, what I have shown here, the coordination number for this atom is 6. Now, please tell me the definition for coordination number. I will give these types of question in the midterm because I want to have you something to write down in the midterm. And that will be very short question. However, you need to write down that type of answers. What is the coordination number? Nobody can. Oh, sorry, I have shown just immediately. So, the number of groups or atoms bonded to one atom. What are the types or how many atoms or groups are bonded to one atom? That is the coordination number. Isn't it? What I have shown here. I have mentioned that this atom is bonded to 6 different atoms. 1, 2, 3, 4, 5, 6. Therefore, the coordination number for this atom is 6, as already I have mentioned. Therefore, the definition is like as the how many atoms or groups. If it can be atoms, sometimes we can have one atom, here atom, or some of them it can be with some group. Therefore, we can consider the number of atoms or groups attached, attached to one atom, that is known the coordination number of that atom. So, if we consider for this one, that is also, this is bonded to this is bonded to this is bonded to this, and this, and this one also this, and this is this. So, it has the coordination number. This is 4 and 2, 6. All of you have forgotten. That's not good. Okay, so in the case of ionic crystal, a structure is stabilized by maximizing coordination number. What does it mean? If you have some crystal of ion, in that case, what you can have? The maximizing coordination number. That means how many atoms are available beside, nearby. If it has the 4 or 6 or 8 atoms of oppositely charged, then it will try to bond up, or it will try to make bond with maximum number of atoms available to the nearby or by the surroundings. So, structures are stabilized by maximizing coordination number and contact between oppositely charged ionic spheres. That means if you have two different ions, let us consider for sodium, and you have chlorine, and you have another sodium. So, two sodium will not attract each other as as strongly as sodium can attract chlorine, because this sodium and chlorine are oppositely charged. Therefore, it's easy to attract the oppositely charged ions with high attraction force. Structures are stabilized by maximizing coordination number and contact between oppositely charged ionic spheres. Usually, larger ions are arranged in a closed packed array, and the smaller cations occupy, sorry, I have mentioned one word wrong, usually larger anions. Anions, that means the negative ions or negatively charged ions. So, in case of sodium chloride, which one is anion? In case of sodium chloride, which one is anion?
Chlorine.
Chlorine.
Yes, chlorine, it should be chloride. Chlorine. So anions, that means the negatively charged ions. So usually larger anions are arranged in a closed packed array and the smaller cations occupy holes. That means closed packed structure. We have mentioned that closed packed structure. So if you have some bigger atoms, maybe consider what in case of sodium chloride, what we have mentioned, if you have sodium chloride, in that case chlorine is bigger in size compared to sodium. Therefore we can have that sodium can fill the holes. If you have some hole in between, in that case the smaller cations will fill up or occupy the as available small holes, and the larger atoms will occupy or it will make the closed pack structure as it is possible. So structure are stabilized by maximizing coordination number and contact between oppositely charged ionic spheres. Usually larger anions are arranged in a closed packed array and the smaller cations occupy holes. And then relative size of opposite ions. Therefore, what are the most important factors to make the structure of ionic crystal? You need to remember this: the relative size of opposite ions. If one atom is very big, another atom is very small, of oppositely charged, as like as hydrogen and chlorine. In that case, if you consider hydrogen chloride or lithium chloride, in that case lithium is very small, chlorine is quite big. Therefore if their size is very different, in that case their attraction force or their where the atoms can reside, mostly as we have mentioned for lithium chloride, the lithium will be at the center or at the hole, because the when the crystal structure, the bigger chloride ions are making making very close packed structure, the available holes will be occupied by the cation, that means lithium. Ratio of opposite ions in compound. Okay, how many opposite ions? If one atom have 5 or 6 negatively charged ions or opposite ions, let us consider for lithium and chloride. If you have 1 lithium and 6 chlorides, then that the structure will be one type. If you have 1 lithium and 2 chloride, in that case the available, that means the ratio of opposite ions, is another factor how the structure of the ionic crystal would be. So a structure of ionic crystal, we can have the maximum coordination number, radius ratio. The ratio of anions and tetrahedral sites is 1:2, and for the octahedral, that means for tetrahedral it become 1:2 and for octahedral 1:1. So that means if you have the structure octahedral, then what would be the ratio of anions and cations? So that would be 1:1. For octahedral sites are larger than tetrahedral sites. Okay, if cations are too large, anions adopt more open structure. That means if, as already mentioned, if the cations are very small, then it will occupy the hole or open spaces. But if the cations are very large, if the cations are too large, anions adopt more open structure. Therefore in that case the anions will have very different type open structure. So coordination number, we have, if we have the coordination number maximum 2, in that case the type of the void can be linear. In that case we can consider that hydrogen molecule, if we consider hydrogen molecule or something like this. So in that case 2 hydrogen atoms have maybe one hydrogen atom here, another hydrogen atom here, and in between there is only one open space. So 2 coordination number and that would be linear. Triangular planar, how it is. If we consider one triangle like this, just these three fingers, so triangular planar like this. So do not consider above the my fingers, just only these three fingers, that can be considered triangular planar. So that types the coordination number can be maximum 3. So that is the example. We have given some close packing. See radius ratio, we don't need to remember all of them, just relationship between radius ratio and coordination number. So you can see, as the radius ratio increases, the coordination number also increases. And you can easily consider, as the coordination number increases, the molecule or the crystal structure will be highly unstable or stable. What would be? If the coordination number is more or large, in that case the crystal would be very high structure, highly stable or unstable. No response. Okay, so we are going to say that if the coordination number is very large, in that case the structure is expected to be very strong. Okay, now sodium chloride structure. Sodium chloride is face-centered cubic structure. This is our small sodium cation, and chlorine very large atom. So what we have mentioned for face-centered cubic structure. Face-centered cubic structure, if we go back, then we can see, first we will have one type of atom at the 8 end or 8 corner. This is one, this is one, this is one, this is one. So in that case we will have this yellow or this cream color can be considered as the chlorine or chloride. Therefore this is chlorine, and the sodium is smaller, so they will be at the face. So here we have one face, here we have one face, and this is, so how many phases we have? 6 phases, is it? If we take the cube again, so we can have one here, we can have one here, we can have one here, we can have one. So we have 6 edges or 6 surface. So if you put 6 sodium atoms at the center of the each surfaces, that would be the structure for sodium, or sorry, sodium chloride. So we have given 8 atoms at the corner, chloride ions at the each corner of the box, and if we put 6 sodium atom at the surfaces, therefore we can have the structure for sodium chloride. And what is the coordination number for this? You can consider, if you have this one, so the coordination number for this, it is
6.
Yes, we can easily find out 1, 2, 3, 4, 5, 6. So face-centered the cubic sodium chloride structure, and already we have shown here the coordination number is 6. Sodium ions in the octahedral voids of the lattice structure made by chloride ions. So how many chloride ions we have? Already 1a, this is upper surface 4 and lower surface 4. So 8 chloride ions making some structure, and all the sodium ions are at the voids of, therefore this is one open space, this is one open space. So here all the sodium ions are at the center. Now we will have very small, I'm not going to show you this one, that is something similar, caesius ion from simple cubic arrangement. Lattice enthalpy, that is very interesting, and it has a very large use, that is kind of mathematical calculation. So what is the lattice enthalpy? lattice enthalpy or Born-Haber cycle. So Born-Haber cycle, we want to know how much energy is required to make one crystal, how much energy is released when one crystal is formed. So crystal is formed, let us consider this is sodium and chlorine. So sodium ion and chloride ion, they are making one crystal, sodium chloride solid. This is sodium in gaseous form and chloride in gaseous form. So ions always need to be in gaseous form. So when 1 mole of gaseous ion, when 1 mole of lattice, this can be considered as lattice, or 1 molecule. One molecule or solid molecule is formed from its elemental ions. Then how much energy is released? That is known as lattice enthalpy. So you may be familiar with the heat of formation. All of you are familiar with the heat of formation? Hello, anyone can hear me? Do you know about the heat of formation? Heat of
Maybe
formation,
forget, Professor.
heat of formation or heat of combustion? Okay, if you do not remember, then just let me. Yes.
Actually, Professor, I am fasting today, so can I go for having dinner? And
Yes.
you can take my attendance now?
Sure, sure. Your Khala.
Yes.
Okay, thank you. I'll give you.
Thank you, Professor.
Okay, okay. Okay, so lattice enthalpy, and as I have mentioned, I wanted to give you the example, definition for heat of formation. So when you are making one compound out of its elemental composition, so if you consider you want to make water molecule, so you need hydrogen gas and oxygen gas. In that case, you want to prepare one water molecule, so you need only one hydrogen molecule and half hydrogen molecule, that means one oxygen atom. In that case you will get one water molecule. So to prepare, or when you are making one water molecule, some of the energy will be released. So how much energy is released when one molecule of any compound is formed in a standard state? That is known as heat of formation. And heat of combustion, that is even easier. Just how much energy is released when 1 mole of substance is burned into oxygen. So if you want to burn hydrogen gas or methane gas, if you want to burn methane gas with oxygen, in that case when 1 mole of methane gas is burning with oxygen, in that case we will get some carbon dioxide and water. Therefore we are burning 1 mole of methane with oxygen, we are getting water and carbon dioxide. Therefore how much energy is released when 1 mole of methane is combustion, or when 1 mole of methane is burned into oxygen? That is the heat of combustion. Now we are coming to our point, the lattice enthalpy. That means when one lattice is formed, from which? From its elemental ions. So if you want to prepare sodium water, or if you want to prepare potassium chloride, in that case you need potassium ion and chloride ions. So how much energy is required, how much energy is released, we will be able to calculate here. So the energy released when 1 mole of crystal or one lattice, that means one molecule, actually one molecule is formed by its elemental ions, that is known as lattice enthalpy or lattice energy. In other way, you can say sometimes you can define the bond energy. As I already have mentioned about the formation, heat of formation, you can define the same thing when how much energy is required to break the bond or to break one molecule. That is the bond energy. You may define like this way. That means the energy required to break one molecule, that is the bond energy. Now if we say in other way, how much energy is released when one molecule is formed, that means the energy will be same. Similarly, here we are mentioning that how much energy is released, that is the energy. How much energy is released when 1 mole of substance or one lattice is formed from its elemental stage. Okay, so when 1 mole of substance is prepared or generated from its elemental ions, therefore that much energy. Now we can calculate how much energy is released when 1 mole of substance is formed. We can calculate by this way. How? See here, we can have, if we start normally we start from our sodium solid. We have in environment we can get sodium as sodium solid and chlorine as chlorine gas. So you need to have, our target is to get sodium plus and chloride minus to get the sodium chloride. So you need to go step by step. How? First you need to make, this is our reactant, initial reactant, let us consider. So sodium solid, in room temperature sodium can be as solid, and then that is half chlorine gas, because we need only one chloride ion. So we will have half into Cl2, so you will get chlorine gas, half chloride, one chlorine atom. Okay, now we want to convert this sodium solid into sodium gas. In that case we need to supply some energy. We need to heat up this sodium solid to gas. That means we need to heat up the system. Now this sodium gas and chlorine gas, half chlorine gas, we want to remove one electron from this. So that means we need to remove the ionization energy. We need to remove one electron from sodium. In that case what we are doing, that we need this mass energy 496, what is the unit, kilojoule per mole. So 496 kilojoule per mole. So when sodium solid is converting into sodium ion plus electron, that means it is releasing one electron, therefore it will require 496 kilojoule of energy. Next step, we are going to have this sodium and then this half chlorine gas. Now we want to make this half chlorine into chlorine atom. This is the chlorine molecule. So we want to make the chlorine atomic. So you need to add more energy, because when chlorine is in molecular stage it has some attraction force. So you need to break the chlorine molecule to make the chlorine gas. Now you have found sodium plus electron plus chlorine. Then what will happen? This sodium plus and this electron will be attracted by this chlorine to form chloride minus. So when this electron is attracted by this chlorine, it releases some energy, because chlorine in atomic level it is not very stable. So when it becomes stable, by gaining 1 electron. Therefore we can have this chlorine can have the 1 electron, and then it becomes more stable by losing 349 kilojoule per mole energy. Therefore that was our maximum energy what we have added from here to here, 107 496 plus 122. This is our energy scale. So now it becoming sodium plus and chlorine minus or chloride minus. Therefore it releasing this mass energy 349 kilojoule. So we are getting that. Now you can see this sodium plus and chloride minus. So they can form this sodium chloride solid by releasing this mass energy. So from here to here. So from here to here it releasing this mass energy. So we are getting the sodium chloride complex or lattice. So now in every step, if you calculate or if you sum up all the energies with sign, then you can have this value is known as the lattice dissociation enthalpy or lattice enthalpy, because this is our left side of the reaction as already have mentioned. So from here sodium plus and chloride minus, we can have the sodium chloride crystal or lattice. Therefore that energy is the lattice enthalpy or lattice energy. So we can calculate how much energy is required or released when the sodium ion and chloride ion is making the sodium chloride crystal. So just if you sum up all the steps, then you will get that the energy is 787 kilojoule per mole. So any of you have any question regarding this? And you may have one question here. I didn't mention this one. Minus 411. What is this? That is the heat of formation of sodium chloride. As already I have mentioned, the heat of formation of water or something else. So when the definition of heat of formation of any compound is when 1 mole of any substance is prepared from its elemental composition. So just this is sodium solid. In room temperature sodium is solid, chlorine is gas. So elemental composition from when we can prepare or when we can synthesis one compound from its elemental stage, that is known as the heat of formation. So now you can calculate the lattice enthalpy just by addition and subtraction all the values, then you will get this mass energy. So any of you have any question regarding this? Now if I ask you to draw a structure for magnesium chloride, if it is possible you can, you don't need to have this value, you don't need to put the value for this 122 349, but the systematic what we will have first, as already we have sodium, then we have make it sodium gas, it was in solid, then we need to make it into gas, and then we need to convert into sodium ion plus electron, then we will have this chlorine gas will be chlorine molecule will be converted into chlorine atom, then this chlorine will gain the electron to form it chloride ion, therefore the energy will be even lower. Therefore from that way, so now if I ask you to draw the structure like this way, you don't need to give the value for this, just if I ask you to write down the steps to make the lattice of magnesium chloride, if it is possible. I can give you this question. If it is possible. Nobody. Do you want me to tell this one? How we can write down, or
Yes, Professor.
how we can calculate the lattice enthalpy of magnesium chloride? In that case, what will happen? We will start from magnesium, solid magnesium, is it? So we will start from solid magnesium and then chlorine. How many chlorine you need? Magnesium chloride, MgCl, 1 or 2 or 3?
2.
2. Okay. Then you need the magnesium, 1 magnesium solid and 1 Cl2 gas. Okay. So our starting is here. Maybe we can go for one white board. We have the whiteboard of just a second. So maybe we can have a whiteboard. Okay. Why? Okay. So we will have that. First we have started with magnesium, solid magnesium, Mgs, and then we will have plus Cl2, sorry, it is not so good to write down, Cl2 gas or whatever, just that is in gaseous state and this magnesium is solid state. So first we need to convert this magnesium solid into magnesium gas. So you need to apply some energy. Let us consider delta H1, that is energy. Then you need to convert into this magnesium to release 2 electrons. So in solid to magnesium it will be converted into magnesium gas. Can you see my display? Can you see?
Yes, Professor.
Okay, so first we will have, or we will start from the magnesium solid and chlorine gas. Then we will have to convert the magnesium solid into magnesium gas. Then we will release 2 electrons. So we will have like this way, Mg2 plus 2 electron plus 2 electron, and then already we have 2 Cl2 gas, Cl2 in gaseous form. So that is our, you need some energy because we want to remove 2 electrons from this magnesium 2 plus, so that will be delta H2. Okay, that is also we need to apply, so that is the delta H is positive, this is delta is positive. Now we want to make this Cl2 chlorine into, this is chlorine molecule, so you need to convert this chlorine into chlorine gas. So what you have to do, so magnesium 2 plus as it is, I am not writing this part, so we need to convert Cl2 gas, then we need to make it 2Cl. Okay, we are converting this chlorine molecule into chlorine gas. Okay, that means atomic chlorine. Then that will also require some energy because we are breaking the bond for chlorine molecule. So delta H3, we will have delta H3. Okay, now this chlorine is in atomic stage and we have minus 2 electrons. So we have 2 electrons. These 2 electrons can be taken by these 2 chlorine atoms. That will make as magnesium 2 plus 2 Cl minus. Okay, so that is our lattice what we need. That means magnesium in solid. That means what we have shown here previously. So we have started from here. First we converted this sodium into sodium gas, then we have converted this sodium plus sodium, removing one electron, then it is converting this chlorine gas into chlorine atom, that means chlorine molecule into chlorine atom. Then this electron is gained by this chlorine, so here we will have magnesium 2 plus 2 electron, and then we will convert into chlorine gas 2Cl atom. Therefore 2Cl atom will gain 2 electron, then it will convert into magnesium 2 plus 2Cl minus. That is the another delta H. So what you will have? So you will have this value energy, another one, magnesium solid plus Cl2, it will convert into magnesium chloride solid. So you will have, this is another value. So that is our lattice enthalpy for magnesium chloride. Okay, any difficulty? Exactly same thing, just only I have changed chlorine gas. Here was half chlorine, but in magnesium chloride we will have 2 chlorine. That means chlorine molecule, one chlorine molecule. Here was half chlorine molecule. That is, so extra diffraction, in last class I have mentioned about this, what we can use for extra diffraction. And not getting, we had something very interesting, atomic force mass spectroscopy, tunneling microscope. So we are not going to show. So if I could explain that one, that is very useful instrument if you have any crystal structure, or if you have some very nanoparticle, very small particles. As already I have mentioned that the different types of face powder or face wash, they are using the nanoparticles. So we can analyze the size of the particles and what is the shape of the particles using these types of instrument. So I could explain, but we do not have very much scope. But if I could have some scope, that I could explain something. So this is the end for today. If you have any question or comment regarding this, then you are welcome. Any question?